Okay, this is Physics, Chapter 13, Part 2. Be sure you see Part 1 before going on to Part 2. I'm sure you have already. This video will include a quiz, a 4-question quiz. And one moment, we have a word from one of our sponsors. All right, now, moving on from there. When you submit your quiz answers to me, I want the subject line to simply say Physics Quiz, and then identify the chapter 13. I think I gave you a quiz in the first part of this chapter, but I don't even remember now. Of course, when I look at your emails, I will quickly see if I did or not, but I don't recall. So I'm going through this just in case I have not told you how to do this before. But in the subject line, Physics Quiz, Chapter 13, and then in the body of the email, not as a picture attachment. No, that's way too much trouble for me and for you. But in the body of the email, simply give me the 4 answers to the 4 quiz questions that I will ask during the course of this video. So, we move on. Hey, tell you what, let's start with one quick question right now. Question number 1. Question number 1 shall be this. What chapter are we in? What chapter are we in? That's question number 1. Yes, these quizzes are not designed to check for your deep understanding of the material, but these quizzes are designed just to make sure that you have actually seen the videos. By the way, folks, don't be silly. Don't try to send the answer to somebody else. Oh, you don't want to watch the video? Here are the answers to the quiz. You're going to come on, make your friends watch the video. Don't do that to them. That's silly. Why would you encourage them to not watch the video? Don't tell your friends what the quiz answers are. That's ridiculous. Make them find the answers for themselves. Gee whiz. It's not like they have to work at it. All they have to do is watch the video. Okay, we move on. Let's see. We're on page 249, and want to look at something pretty cool here. First of all, not quite ready for that. Think. Suppose we have a container, as illustrated on page 249 at the bottom of the page, a container of water, and we've poked some holes in the side of this container. Water is going to spurt out of all 4 holes. But where is the pressure the greatest? Remember, pressure in a liquid depends only on the depth. How deep are you in the liquid? So that means we're obviously going to have the higher pressure at the bottom of this cup. So at the bottom of the cup, the water is going to spurt out of this hole kind of like this, perhaps. Now up here, there's less pressure. So the water here is going to spurt out more like that. Here, there's even less pressure, so the water might spurt out kind of like this. And here there's very little pressure, the water might just be dribbling out like that. It's going to squirt out farther on the bottom holes. But here's a very important concept. When it exits the holes, it will always exit initially perpendicular, you can't see that. It will always exit perpendicular to the surface. Because the pressure on the sides of this container, the net pressure on the sides, is always perpendicular to the surface. Because the pressure is always perpendicular to the surface, the water when it first comes out will always be moving perpendicular. That's why the water doesn't squirt out in some weird direction. It'll squirt out perpendicular to the surface. Same thing with a boat. What happens if you're in your canoe? Here's your canoe. That looks like it's sinking already. Let's fix that. Here's your canoe. Oh, that's a pitiful canoe. And you got a hole in the bottom of your canoe. Oh no, there's a hole. Well, what's the water going to do? Because the pressure is transmitted equally in all directions, it's going to be squirting straight up out of the hole. That's squirting water. It's going to squirt straight up. If the pressure were not being transmitted equally in all directions, if it were only down, then the water would not come into your boat at all. But the pressure is against all the sides equally perpendicular to all the sides, it's going to squirt straight up. If you had a hole here, oh no, we got two holes, then it's going to squirt out like this. It's going to start off perpendicular to the surface and squirt out that way. All right, we move on. Oh, there's so many. This chapter is full of cool things I could show you, and I forgot to bring a source of clean water to do some demonstrations. So we're going to have to wait for part 3 for some of my favorite demonstrations. I'll tell you though, my all-time favorite chapter 13 demonstration is one that I invented myself. But you're going to have to wait for reasons I'm not going to try to explain. It's going to be in chapter 14, where in chapter 14 we're going to back up in the very first segment of chapter 14 and see a really cool demonstration of air pressure supporting water, combined with something at the end of this chapter that we haven't quite gotten to yet. So one of the chapter 13 demos, at least one, will be in chapter 14, so hang tight for that. Now, buoyancy. You know about buoyancy. You've got your little brother in your arms, and he's trying desperately to get away, but you're stronger than he is, and so you've wrestled him into your arms, and he's kicking and screaming, and you're like, Mom, Mom! But Mom's far away, she can't hear. And you take him, and you're going to the pool, and your backyard pool, and you're thinking about throwing him in, but you think, no, that's not enough fun. I'm going to actually go down the steps of the pool, because we have this nice neat step thing going down there, and I'm going to step down in there with him, and I'm just going to carry him down into the water. Well, right now your brother is pretty heavy. He weighs like 40 pounds. He's a little guy, but he's 40 pounds still, and you're kind of struggling to hold him. You get into the water, and as you and your brother get down into the water, what happens to his weight? All of a sudden, he becomes very easy to hold. He loses almost all of his weight. It's like holding nothing under the water there. What's going on? Well, that's called buoyancy. If you take a piece of, a typical block of wood, it's not true of all woods, but take a typical piece of wood and put it into a container of water, what's that wood going to do? It's going to float on the surface. Why? Buoyancy. You have an ice cube. An ice cube would do the same thing. An ice cube is going to float in the water. Why? Buoyancy. Now, if I ask you, what is the root cause of buoyancy? Everybody says, oh, that's easy. We learned this back in elementary school. An object will float if it's less dense than water, whatever that means. Yeah. If it's less dense than water, it'll float. If it's more dense than water, it'll sink. That's a gross oversimplification. We need to have, why does that happen? Why, if it's less dense than water, does it float? Why, if it's more dense than water, does it sink? Why? Not just does it, but why does it? The answer is shockingly simple. Let's have an object that is immersed in water. By the way, the physics definition of immersed, it doesn't have to be all the way under to be immersed. This object is immersed. This object is also immersed. Now this one is submerged, and that one's not submerged. For instance, that's a boat. A submerged boat is not a good thing. But it's immersed. It's in the water. It's immersed. These are both immersed. So we have any object that's immersed in a liquid. Here's the cool thing. Notice, please, and you're going to love how simple this is. This part is deeper in the water than this part. That means there's more pressure on what? More pressure on the top or more pressure on the bottom? Well, there's going to be more pressure on the part that's deepest in the water. So there's more pressure down here. There's less pressure up here. If there's more pressure down there and less pressure up here, what's the net upward force? Yeah, up. That's called the buoyant force. So we have a net upward buoyant force. Now what determines whether this thing's going to rise or fall? Well, it's always going to rise, isn't it? No. This is just the buoyant force. What about the weight of the object itself? Let's do the weight of the object in weight. We have a certain amount of upward buoyant force. What if the object itself weighs more than the upward buoyant force? Oh, If the object weighs more than the buoyant force, the object will sink. It'll feel lighter because you have to subtract from its weight the upward buoyant force, but it's still going to go down. On the other hand, what happens if your object weighs less than the buoyant force? The buoyant force is bigger than the object's weight. Then the object will rise to float. Pretty cool concept. Now let's add to that Archimedes' principle, which is on page 251. Archimedes' principle, first of all, to prep ourselves for Archimedes' principle, if I have here a flask with a little lip thing on there, and I fill it all the way to the top with water, and then I put a mass into the water, won't that cause some water to spill out? Sure. And I could capture that water that spills out. Capture, 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 splish, splash, water splashing into here, and we get all this water in here. This water is called the displaced water. That is the displaced water. The water that was pushed out of place, displaced, pushed out of place by the object when the object went in. The volume, the volume of displaced water will be equal to the volume of the object you put in there. Now, Archimedes' principle says this. The buoyant force upward on the object will be equal to, get this is so cool, the buoyant force upward on the object will be equal to the weight of the displaced water. If this thing went in here and displaced 10 newtons of water, then the buoyant force will be 10 newtons. Archimedes' principle. So suppose for a second that we put this thing in here, and indeed 10 newtons of water was displaced. If 10 newtons of water was displaced, then the buoyant force must also be 10 newtons. Now suppose the object is a rock, and it actually weighs 20 newtons. Well, if the object weighs 20 newtons, but the displaced water is only 10, meaning that the buoyant force is only 10, but the object weighs 20, the net force is how much and in what direction? Yeah, 20 down, 10 up. There's a 10 Newton downward net force. The object will sink. On the other hand, suppose this thing is made of some other material like styrofoam or something, and suppose the object itself only has a weight of 5 newtons. It's a very lightweight object. If it weighs 5 newtons, it's still displacing the same package of water. It's still displacing the same amount of water. That displaced water still weighs 10 newtons. So the buoyant force is still 10 newtons, but the object only weighs 5 because it's made of some lighter weight material. Therefore, we now have a net force upward of 5 newtons. So this object is going to rise to float. Pretty cool. What happens if the object, same size object, it's still displacing a package of water with a weight of 10 newtons. Therefore, the buoyant force is still 10 newtons. That's Archimedes' principle. Suppose the object itself weighs exactly 10 newtons. The weight is 10 newtons. Well, what happens to its 10 newton weight and the 10 newton buoyant force? They cancel. Therefore, where's it going to go? No place. Have you ever tried taking a water balloon into the pool? Hey, you could take the water balloon, make a small water balloon and put it in a sink full of water in the kitchen. Same thing. Where's it going to go? It's going to go nowhere. It's going to hover wherever you put it. Now, yeah, I know the rubber part of the balloon has some weight to it, and that might mess up the experiment some. But basically, yeah, you put a water balloon into water, it's going to displace a certain amount of water, but the displaced water will weigh the same amount that it weighs. So if the object has the same density like water and water, the same density as the displaced water, it's not going to go anywhere. You ever seen these pool toys? They're kind of shaped like this, and they've got fins on them, and I think it's called a torpedo. I don't know. And you put it down into the water, and it's designed to be the same density as water. It's designed to displace its own weight in water precisely. Therefore, the buoyant force is equal to its weight, so you put it in the water and it goes nowhere. These things are really cool because then you can take it underwater and throw it underwater, and it will scoot right across all the way from one end of the pool to the other and bop your friend in the leg or whatever, and he goes, "Oh, what was that?" And you're laughing hysterically because you shot him with this torpedo by throwing it underwater. It doesn't go down, it doesn't go up, it just goes straight. Because its weight has been canceled by the buoyant force, so it goes straight across that pool all the way. Pretty cool. I had a chance to play with one once, years ago. They're neat. Kind of heavy, because it's equal to the weight of an equal amount of water. And it's got some good heft to it. All right, what happens though? Let's consider this. What happens if I have an object that weighs, say, 5 newtons, and it's displacing, splish splash into my little beaker here, it's displacing let's have this displacing 10 newtons of water. So the weight of the water is 10 newtons, therefore the buoyant force is 10 newtons, but the object only weighs 5. We now have a net upward force. The buoyant force wins. It rises. What happens when it rises to a point where, let's rise all the way here, it has risen, 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 it has a weight of 5 newtons, but wait just a moment. Now it's partway out of the water. It's no longer displacing a full 10 newtons of water. It's halfway up. Now it's only displacing 5 newtons of water because it's partway out of the water now. So that means that the upward buoyant force is 5, the downward weight is 5. What's it going to do now? And chances are what you're thinking is going to be wrong because I love this question. Oh, it'll stay right there. No, it won't. What's the net force? 0. Right. What does F equals ma say happens when the force is 0? The acceleration will be 0. Acceleration, not speed. That means that as it rises and hits that point where we are in equilibrium, what's it going to do? Inertia says it's going to keep going. There's no net force. Haha, yes. So it keeps on going. It keeps going. Now it's sitting maybe up like this. Now it still weighs 5 newtons, but now look, it's only displacing 2 newtons of water. So now the buoyant force is only 2 newtons. So now the downward force wins. So what's it going to do? It's going to kind of bebop up and down, up and down, up and down, until finally it hits that equilibrium point where the displaced water weighs the same as the object itself. But it doesn't just go up here and stop, it goes up here and bebops. Have you ever had a case where you have like a beach ball and you've managed to push it all the way under the water and you release it? Does it go to the top and just suddenly stop on the top like that? No, what's it do? If you push it down far enough, it pops up into the air and then comes back down and rests on the water. So yeah, it continues moving past that point of equilibrium because of inertia, and eventually it will find a point of equilibrium where the displaced water equals its own weight. Now, that pretty much, a very important little detail in the sidebar, page 252. Important detail is that 1 liter of water, what's 1 liter of water look like? Interesting that in most of the metric system, like what does a meter have to do with a yard? Well, a meter is a little bit longer than a yard by a few inches. What does a centimeter have to do with an inch? Well, a centimeter is a lot smaller than an inch. A kilometer compared to a mile, they're very different. But interesting thing is that a liter is almost equal to a quart. Very, very close to being a quart. So a quart and a liter happen to be almost the same. This is a quart-sized jar. This was a quart of kosher dill pickles. And it says it contained 1 quart of pickles. Okay, so that's what 1 quart looks like. If I fill this with water, 1 quart, or let's use liters, 1 liter of water has a mass of 1 kilogram. Therefore, if you remember how this works, how do I get weight out of kilograms? Kilograms is not weight, kilograms is mass. How do I get weight from kilograms? You multiply by G. Are you going to use 9.8 for G, or are you going to use 10? That's up to you. We'll use 10. So 1 liter of water has a mass of 1 kilogram, and therefore has a weight of 10 newtons. So 1 quart of water, 10 newtons. Nice fun fact that could come in handy. Wow, that takes us all the way through the end of page 252. Wow, that takes us through 253. Cool. How do boats float? Well, a boat floats because it's able to displace, here's the displaced water, it's able to displace an amount of water equal to the boat's own weight. How can an aircraft carrier float? What's an aircraft carrier made of? And most folks say, oh, I think it's made of steel. Steel's really heavy, so what's up with that? No, I would argue that an aircraft carrier is not made mostly of steel. An aircraft carrier is made mostly of air. The steel is shaped in such a way that it traps all this air in here, and so it's able to displace a whole bunch of water here, and it's able to displace an amount of water equal to the ship's own weight. In fact, when they talk about the weight of a ship, they don't say, oh, this ship weighs 20,000 tons. No, they don't say it weighs 20,000 tons. They talk about a ship's weight in terms of displacement. They say, oh, the ship's weight is 20,000 tons of water displacement, or I've forgotten the exact language they use, but they talk about a ship's displacement more than its weight. In fact, in World War II, when the Germans were really into using submarines to shoot down our ships, and they were shooting down just about anything that floats, before they got really desperate, their submarines would be hunting down oil tankers that were full of oil because they wanted to damage our oil supply. So they didn't want to risk being found. Every time they launch a torpedo, they become visible. You can see the bubbles from the torpedo going through the water, and everyone knows, oh, there's a torpedo. Oh, that must be a submarine. Oh, let's go get the submarine. So they're revealing their location if they fire a torpedo. So they save their torpedoes for good targets. They don't want to shoot at an empty oil tanker. Why risk getting caught doing that? They want to fire their torpedo at a full oil tanker. How do they know the difference? Well, a full oil tanker is going to sit down deeper in the water. An empty oil tanker is going to sit up high in the water. So they're going to go for the full oil tanker, and they're probably going to let the empty oil tanker go until they get to a point where they're really desperate. They start shooting down anything they can find. It was incredibly dangerous. I've forgotten, I saw a video about this once on YouTube, how dangerous it was to be on the crew of a German submarine. Their chances of surviving the war if they were on the crew of a German submarine, very, very slim. Most of them, I don't know if it's most, a whole bunch of them. I mean, the mortality rate of submarine crew members was very, very high. Worse than coronavirus by far. Yeah, you've got two choices. You can be on the crew of a submarine in World War II, or you can get coronavirus. I would take corona. All right, moving on. Well, or should we move on? Maybe I should stop there. Now, one more thought. There is the flotation principle. Flotation principle is on page 255. I haven't been asking any quiz questions. I need to throw in another quiz question. Quiz question. How about this? Question number 2. Quiz question number 2, the answer is 2. Quiz question number 2, the answer is 2. Write it down, email it to me later. We'll come up with quiz question number 3 here in a few moments. Oh yes, the flotation principle on page 255. Flotation principle is as follows. That any floating object, any object that's actually floating, such as this boat, whatever it may be, any floating object will displace its own weight of water. Think about it for a moment and that becomes obvious. If it's floating, where is it going? No place. So if it's floating, what's the net force? 0. Right. If it's floating, the net force must be 0. That means that its weight downward must be equal to the buoyant force, because the net force is 0. That means that it must be displacing its own weight of water, because the displaced water weight equals the buoyant force. And if the buoyant force equals its weight, then any floating object will always displace its own weight of water. Hey, you know what balsa wood is? Super, super lightweight wood. You lay balsa wood on water, a person might think that if this is the surface of the water and I lay balsa wood on there, that it floats like this. No, that's not possible. How much water is this displacing? None? Yeah, if it's not displacing anything, then it's going to have to go down. There's no buoyant force. So even balsa wood has to displace something. In order for it to float, it has to displace its own weight of water. If this balsa wood weighs 3 ounces, then to float it has to displace 3 ounces of water. There's no such thing as an object floating exactly on the top like that. Not unless, when Jesus walked on water, it wouldn't surprise me, he probably walked on it like that. I don't know. But that was a miracle. We're not talking miracles here, we're talking Archimedes' principle. When you buy a submarine. What? If you buy a canoe, buy a submarine, that'd be nice. If you buy a canoe, most likely inside that canoe there's going to be a yellow and black and red sticker that warns you what the maximum weight is. Pay attention to that sticker. Because if you go past the max, suppose it says this will support 200 pounds. Okay, if you put 250 pounds in that thing, the shape of that boat probably is not sufficient to be able to displace 250 pounds of water without itself going under. They're telling you how much water that thing can safely displace. More than that, and it's going to have to go bloop, bloop, bloop to the bottom. So those stickers are based on buoyancy of water and based on displacement. How much water can that canoe displace before you find yourself with water going over the edges? Okay, we're going to stop there. That brings us to, for next time, we'll pick up on where? Wow, that brings us all the way to, whoo, look at us. We are about to launch into page 257, and it's not inconceivable that we might actually finish the chapter in the 3rd video. Wow, just a 3-video chapter? We'll see. So next time, we pick up on page 257. Have a good rest of your day, or your evening, or whatever it may be. Farewell. Oh, quiz question. How many have I given you so far? 2 quiz questions? All right, I'm going to go ahead and cram in 2 more. No, let's not. We'll just make this a 2-question quiz. This one will be only worth 2 points. It'll be a warm-up quiz. So this is a 2-question quiz. I've already asked you both questions. Just please write them down someplace, and when you finish the video, send me an email, you already saw, where was that? Do I still have it here, or did I kill it? There it is. In the subject line, write physics quiz, chapter 13, and then give me the 2 answers that we have seen. Well, I've already forgotten what they were, but when I see your emails, I'll be quickly reminded what they were. I know what that one was. I don't remember what that one was. I don't remember, but you'll tell me. Okay, we're done. See you later. Bye.